On to chapter 6. Here in chapter 6, just like in chapter 5, we're concentrating in on covalent molecules. Okay? And remember, the reason that we're really concentrating in on covalent compounds and covalent molecules is that the vast majority of compounds are covalent in nature. So that makes them super important to us understanding chemistry. Okay, most of the chemistry is chemistry of covalent compounds. So we finished up Vesper, and Vesper says that electron groups repel each other around a central atom. Okay, and space out as far apart as possible. Vesper doesn't tell us how. How do these atoms with their bonds take up the shapes that we see in Vesper? Okay? So we need an explanation of how. How do electron groups around the central atom spread themselves out the way they spread out? And how can we make this work with quantum mechanics and the atomic valence orbitals of the atoms before they bond? Now, thinking about this, we need to remind ourselves about the shapes and the 3D positions of atomic orbitals relative to each other. Okay? Remember that p orbitals lie along the x, y, and z axis. The s orbital is a sphere. So let's just think about s and p orbitals here for a second. Now I'm going to draw a picture and I'm going to show it to you. I'm drawing, guys. I'm trying to do my best. Okay. Now, let's come over here and let me draw things for you. Okay. Now, there's s orbital. Okay. If I were to draw the p orbitals, one would sit here. One would sit here. And one would sit here along the x, y, and z axis. Okay? They're at these angles from each other. Now let's think about it. If I just looked at this lobe of this p orbital and this lobe of this p orbital, they're 90 degrees from each other. The lobe here and the lobe here are 90 degrees from each other. The s orbital is just a blob around all of them. If we start to look at doing bonding, one of the things that they realized looking at the geometrical arrangement of the s and the p orbitals relative to each other is that when atoms bond, they have to do something wonky with their valence electrons. Because when they think about bonding, they think about an orbital from one atom coming in and overlapping with an orbital from another atom to form a bond. If you did that with the atom's original valence orbitals, and let's say I made bonds and they overlapped with p orbitals, I would get 90-degree angles. Say if I made 3 bonds, I'd have an angle here, an angle here, an angle out here. They'd all be 90 degrees from each other. And that's not what we see. So there has to be some explanation that can explain the shape. And our first attempt, well, our attempt to explain the shape of a 3-dimensional molecule that we see in Vesper is something called valence bond theory. Okay? So let's look. If we were to look at the orbitals, when 2 atoms come together to bond, like in methane, CH4, we know that there are all single bonds between the carbons and the hydrogens. The logical way to think about this is taking overlapping orbitals. Okay? Well, one of the first things we know is if we look at the electron configuration for carbon, in an unbonded carbon atom, there are 2 unpaired electrons. The carbon is making 4 bonds. When Lewis did his Lewis dot symbol, it had 4 unpaired dots. Okay? So one of the things that we know has to happen for carbon to bond to those 4 hydrogens is that carbon has to spread out its valence electrons. Okay? One of the electrons in a 2s orbital has to jump out to a 2p. So the carbon goes into an excited state before it bonds. Okay? And then if we think about doing the electron-electron orbital overlap, well, I'm using an s subshell from hydrogen. That's the only one it's got. But now in the carbon, I have an electron in an s subshell and an electron in 3 different p subshells. That would give me 3 bonds that were 90 degrees off from each other and 1 bond that's going to be at some wonky angle. And I'm going to have p and s orbital and s and s orbital, and I'm going to get weird bond lengths, 3 bond lengths that were the same and a bond length that was different. But what we see in methane is that all of the carbon-hydrogen bonds are the same length, and all of the carbon-hydrogen bonds are the same strength, and they're all 109.5 degrees off from each other. So that tells us right off the bat, not only does the carbon atom have to go into an excited state, but it evidently does some remodeling of its valence when it gets ready to bond. Okay? So, to get the shapes that we see, there must be some type of change in the valence orbitals of the bonded atoms versus unbonded atoms. And when we're talking about valence bond theory, we're concentrating in on the central atom. So the new theory to help explain these shapes is valence bond theory, and you'll see people refer to it as VB. VB for valence bond. Now let's go over the points here. Okay. First, the covalent bond is the result of valence orbitals of 2 atoms overlapping each other with a shared pair of electrons occupying the region of overlap. Okay? So, orbital from atom 1, orbital from atom 2, they overlap. And the electrons exist in that region of overlap and run back and forth between the 2 nuclei. Electrons in the shared space must have opposite spin. The more overlap between the orbitals, the stronger the bond. So the closer the nuclei can get to each other, the more overlap they can have, the stronger the bond is going to be. Valence orbitals in bonded atoms must be different than the valence orbitals in... Let me try this again. I ran out of battery. Main points about valence bond theory are as follows. Covalent bond is the result of valences of 2 atoms overlapping, with the shared pair of electrons occupying the region of overlap. Electrons in the shared space must have opposite spin. The more overlap between orbitals of the 2 atoms, the stronger the bond. And valence orbitals in bonded atoms must be different than valence orbitals in unbonded atoms. These new orbitals in bonded atoms should allow for more overlap due to the fact that the electron groups will be more spread out. The new valence orbitals are made by blending together the original valence orbitals within the atom to make new valence orbitals of different shapes and 3D orientations. These new orbitals are called hybrid orbitals. Okay? These new orbitals called hybrid orbitals are made by blending together the original atomic orbitals, and an atom makes only as many hybrid orbitals as it needs to get maximum spacing for electron groups. Think energy. It takes energy to go into an excited state. It takes energy to remodel the valence. What this means is that the valence of an atom could have a mixture of hybrid orbitals and original atomic orbitals. Turns out that the second bond and third bond between 2 atoms do not need hybrid orbitals, because remember, they don't have their own unique orientation in 3D space. The second bond between 2 atoms has to be parallel to the first bond between two atoms. Same thing, the third bond between two atoms has to be parallel with the first and the second bond between two atoms. Okay? So a hybrid orbital is used to make the first connection between two atoms, and the second and third bonds are going to use unhybridized orbitals. Okay? Now, big note, remind you one more time. An atom's valence can contain a mix of hybridized orbitals and unhybridized orbitals. The first bond between two atoms requires a hybrid orbital. The second and third bond do not. Also, lone pairs need a hybrid orbital, just like the first bond that an atom makes to another atom. Because remember, lone pairs have their own location and take up space around a central atom. Vesper said all electron groups, count in trying to spread out around that central atom. So since valence bond is trying to explain Vesper, lone pairs are going to have a hybrid orbital. Okay? So, we're going to look through our situations. Okay, we know that around a central atom we can have 2 electron groups, 3 electron groups, 4 electron groups, 5 electron groups, and 6 electron groups. So we can have 6 different rearrangements of valence orbitals. If we start out with beryllium dihydride. Beryllium dihydride, I know it looks like we've got a metal and a non-metal, and it should be ionic, but in reality it's covalent. The beryllium has 2 valence electrons in its 2s subshell, and the hydrogens have 1 electron each in their s subshell. Okay, so when beryllium gets ready to bond, the first thing, of course, that has to happen is that the valence electrons have to spread out. Now, I'm going to kind of show you a picture here. So we have beryllium dihydride. Looks like that. If I look at the beryllium, because that's my central atom and that's what I'm interested in, its electron configuration is 1s2, 2s2. Okay, now this is core. So we're just going to concentrate in on the valence. So step 1 towards bonding is that we're going to take one of the 2s electrons and move it into a 2p. Now I have the electrons spread out. Then there's going to be a step 2. The hybridization. We're going to take the 2 rooms here, the 2s room and the 2p room, and we're going to blend them together. And we're going to get 2 new rooms called sp hybrid rooms. Okay? So I've now in the valence got the sp hybrid rooms, and I've got 2 undisturbed p rooms. Those 2 electrons now occupy the sp hybrid valence orbitals, 1 in each one. Hund's rule still applies. Okay? Now, this sp hybrid orbitals, they're somewhere in energy between an s and a p. They're about 50-50, well, they're 50-50 each, so they're about smack dab in the middle. Okay? So when beryllium, when I take an s orbital and I blend it together with a p orbital, what we get when they do the math as two orbitals that look like this, a big fat lobe and a little lobe, and they're 180 degrees apart from each other. Okay? So the beryllium sits here and it's got its orbitals like this, and then hydrogen comes in, and it doesn't have to hybridize anything. It's only got one electron and it's in 1s. So hydrogen here uses 1s, and beryllium uses an sp, orbital to overlap. And here's that region of overlap, and that's where the shared electrons would be. Okay? So there's one electron from the hydrogen in here, one electron from the beryllium in here. Okay? So, sp hybridization. So anytime you have two electron groups around the central atom, you get sp hybridization. Now I have pretty pictures, okay, in the notes, but if I don't draw it, I talk too fast. So you can see here an S and a P blend together to give us a mixing. I get sp hybrids, big loop, okay, a lobe for bonding, and then we have the two empty sp. Each one of these sp has one electron in it. So there's more pictures. Okay, you can see that sp here, and the chlorine, because it's not a central atom, just uses its 3p orbital. Okay. 180 degrees apart from each other. Now, if we go to carbon dioxide, okay, the central carbon has two electron groups around it, and they're double bonds. The first bond between the carbon and oxygen, okay, is going to be with is because they're two electron groups, the hybridization has to be sp. The second bond between the carbon and an oxygen is made with unhybridized orbitals. Now let me draw you some pictures. So carbon dioxide. Okay? Let's look at the carbon. So here's my carbon. Okay? I have my sp hybrid orbitals right here. And I'm going to have an oxygen over here and an oxygen over here. And there's p orbital overlap. So for the carbon, that first bond, I'm using sp, and I'm using an s orbital here. Okay? Now, when it comes to the second bond between a carbon and an oxygen, well, there's a p orbital sitting there, okay? And there is a p orbital sitting here. Now, I've drawn mine a little far apart, but what happens is that these guys connect up. Okay? This is called a pi bond. Okay, or you could see pi bond. And this is due to side overlap of unhybridized orbitals. Okay? When I come over here, there's going to be a p orbital that sits like this, and there's the other p orbital in the carbon. They're going to blend together like this. This is also a pi bond. Okay? So in a double bond, okay, the first bond between two atoms, because of end-to-end overlap, is called a sigma bond. So it's end-to-end overlap of hybrid orbitals. For the central atom. So it's end-to-end overlap. So in a double bond, I have one sigma bond, and there's the symbol for sigma, and one pi bond. So a double bond, this bond right here, okay, is a double bond. It's a sigma and a pi. Now let's look at the pretty image I have on the screen. If we look at this guy, C2H2, there's my two carbon atoms, okay? Each carbon is connected to two other atoms. This carbon is connected to this hydrogen and is connected to the other carbon. There's a triple bond between the two carbons. So there are two electron groups around that central atom. It's linear. If it's linear, it has to have two hybrid orbitals, SPs, okay? There's the sigma bond between the hydrogen and the carbon, where the hydrogen's using its 1s orbital to overlap with an sp orbital for the carbon. Same thing over here. The two carbons, their first connection is an sp hybrid orbital overlap to give me a sigma bond. Now, this and this right here is 2p unhybridized orbital overlap to form the first pi bond, and then right here and behind, that's where we get our second pi bond. Okay, so sigma down the middle, pi here, two pieces, pi there, two pieces, and this is kind of just a space filling model, and there's its Lewis dot structure. Okay? So, a double bond or a triple bond, well, a triple bond involves one sigma and two pi bonds. Okay? But again, that's something that's linear. Come on. So, I've written it out in the notes. First bond between two atoms is the sigma bond, and it's due to end-to-end overlap of hybrid atomic orbitals, or a hybrid atomic orbital with a regular orbital in an external atom, okay? This allows for lots of overlap and connection between the two atoms. Okay? To make a second bond, we used unhybridized p orbitals, which are sticking up and below the plane and to the left and right, or front and back of the plane of the carbon-carbon sigma bond, like we were seeing in the C2H2. The best type of overlap we can have is side by side, and it comes in two pieces. It's not quite as good as the sigma overlap, which is end to end, a stronger connection. So that second bond is called a pi bond. So in Be and He2 and in carbon dioxide and something like hydrogen cyanide, we see sp hybridization. 2 electron groups around the central atom means that the hybridization is going to be sp. All right, now let's talk about 3 electron groups. Okay, with 3 electron groups, such as boron trihydride or CH2O, we need to space out 3 electron groups around the central atom. So we need to spread out the electrons and blend together 1 s-type and 2 p-type orbitals for the central atom to give us a hybridization called sp2. Notice 1 s and 2 p's. 1 plus 2 is 3. We blended together 3 orbitals. Okay, that leaves 1 p orbital in the valence that wasn't touched, wasn't used in the rebuild. So in boron trifluoride, okay, you can see that the boron hybridizes 1s and 2 p's to give us sp2 hybridization. And notice that when you do that, mathematically you get that trigonal planar shape. So the borons are using sp2 hybrid orbitals, and the fluorine, being a terminal atom, no hybridization, it just uses its p orbital that only had 1 electron in it to bond. So one of the things to keep in mind here, okay, notice that the sp2 hybrid orbitals are higher in energy than the 2s for boron, and lower in energy than the 2p, but since I used 2 2p's and 1s, it's now closer in energy to p than it is to s. So here in C2H4, you can see that each one of the carbons has 3 electron groups around it. There's a double bond between the 2 carbons. So the first bond between 2 carbons is 2 sp2 hybrid orbitals. The second bond is a pi bond between unhybridized p orbitals. When we have 4 electron groups, we need to have 4 hybrid orbitals. So we're going to blend together a 1s, 1 of the s orbitals, and 3 of the p orbitals, all of the p's. So we get sp3 hybrid orbitals. So if we look at CH4 or water, remembering that lone pairs take up hybridized orbitals just like bonds do, 4 electron groups, we're going to have a hybridization of sp3. So here's the carbon in methane, CH4. Okay? So we use sp3 to overlap with the 1s in hydrogen. Here's ammonia. Notice that one of the hybrid orbitals is occupied by a lone pair of electrons. So in that hydrogen-carbon bond, the hydrogen's using a 1s orbital to overlap with an sp3 hybrid orbital for nitrogen. Okay? And the lone pair is occupying an sp3. And then there is water. And you can see that 2 of the sp3 hybrid orbitals are occupied by lone pairs. So when we get to 5 electron groups, we need 5 orbitals. Okay? That means you're going to need to go beyond the s and the p subshells. You're going to need an outer shell that has the d subshell. That doesn't occur until shell number 3. In shell number 3, you now have a d subshell. And if you're looking at the nonmetals, on the 3rd row, the 4th row, the 5th row, the 6th row, the 7th row, Their D subshell in their outermost shell is sitting there, but it's empty. Okay? So you can expand out into there without any problems. So to create 5 new orbitals, we need to blend together 1 s-type, 3 p-type, and 1 d-type. So it's called sp3d1, or sometimes it's just written sp3d. Okay, I think your book doesn't put the 1 over the d. So here's what it looks like. We blend together 1 s, all 3 p's and 1 of the d's, and then we get 5 identical hybrid orbitals, and lo and behold, they give us that trigonal bipyramidal shape. Okay, so phosphorus pentachloride is the example shown to you. And then if we have 6, we're going to blend together 1 s-type, 3 of the p-types, and 2 of the d's to give us sp3d2 hybridization. Notice now that I'm blending together 2 d's in that we get an energy that's on the upper side of the 3 p's. So it's close, you know, it's starting to inch closer to d's. Sulfur hexafluoride is our examples here. So here's the table, okay, magic table. If you have 2 electron groups so that it's linear, its hybridization is going to be sp. There's going to be 2 sp hybrid orbitals and 2 unhybridized p orbitals in the central atom's valence. Trigonal planar, I'm going to have 3 sp2s and 1 p unhybridized. In tetrahedral, sp3 hybridization, no unhybridized valence orbitals. In trigonal bipyramidal, we're going to have 5 sp3d hybrid orbitals and 4 unhybridized d orbitals. In octahedral, we're going to have 6 sp3d2 and 3 unhybridized d. So 2 electron groups, sp, 3 electron groups, sp2, 4 electron groups, sp3, 5 electron groups, sp3d, 6 electron groups, sp3d2. Now, I think that's a good place to stop. And we'll pick up there and we'll do some example problems out of the book using this. Okay.